So today on the bench we have a wounded HP8664A, which I bought on the cheap at the flea market to replace our Apollo transmitter in case we have to get that one back to the collector that owns it, the original NASA one. And of course it has a fault, that's why it was cheap. Hello and welcome back. If you follow the channel, you know that we are restoring the entire Apollo S-band communication system. In episode 11, we got hold of the ground S-band transmitter that we were missing all along, a glorious golden box of NASA and Motorola goodness, loaned to us by a generous collector. It had been modified after the Apollo program, so we had to reverse engineer it and restore it to its Apollo configuration, which kept us entertained for a few episodes. But we succeeded, and it has served as our trusty Apollo ground transmitter ever since. However, this was a temporary loan arrangement, so I wanted to have a backup in case we have to give it back. Unfortunately, laboratory-grade microwave generators that support both S-band and high-speed phase modulation are neither common nor cheap, even used. So when I saw an HP8664 on sale for only $150 at our local electronic flea market, bless Silicon Valley for that, I had to get it. It came from a professional refurbisher of test equipment, so I was pretty sure it had a failure that the refurbisher was unable to repair. And given that a refurbished one is worth several $1,000s, they must have given it their best try. As a reminder, the thing cost an eye-watering $28,890 when new in 1992, plus $4,375 for the low noise option, which our instrument has. So, quite unsurprisingly, when I turned it on, it spent 15 minutes trying to calibrate itself unsuccessfully. However, once it gave up and spat out a cryptic error message, I was able to tune it to the 2.10640625 GHz Apollo frequency, and it transmitted without problems. That was already a win. Still, it is very annoying to have to wait 15 minutes every time you turn it on, and partially faulty measurement instruments are not welcome in my lab. So let's attempt to repair it. There is just one problem. This is a more recent instrument appearing in the 1992 catalog. By that time, HP had stopped providing component-level schematics and instead relied on extensive self-test capabilities and module-level replacement, which is all fine and dandy until they stop selling or repairing the replaceable modules. They should release the schematics once this happens, but good luck with that. So, as you will see, this is going to be way harder than it should be. And we were trying to get the cover off, and that's when we discovered that you have... How many screws did you say it was?
I think 48.
48 screws. This is built like a tank. And yes, yep. It slides. Okay. Ooh,
oh man!
At least you're rewarded with something. And yeah! Wow, there's a gasket in there. I'll show you. There's a copper gasket.
So they actually did need a gasket.
In an RF gasket.
Right.
So I think this is all for RF protection. So one of the first repairs on the channel was the 8661, which is the granddaddy of that one. Oscillator up to 1 point something gigahertz. This one goes up to 3. And the advantage is that, of course, up to 3 covers 2.1064, 2.025, the
right.
Apollo frequency. And we tried it, actually it works on the upper frequency too. But it doesn't, not all the functions work. So there's a, oh, those are large boards. Mm-hmm. And it's modern, scary stuff. Over there, Surface Mountain Company. And here you can see at the bottom of the case, the EMI copper seal. So I'm going to turn it on. It has a processor that works. And I suppose it's going to go into this calibration loop because it was off for a while. If you see it has a little dot that moves around. Okay, so probably see you in 10 to 15 minutes from previous experience.
15 minutes later.
So it finished and give us a result code of
5053311.
and it's a positive code, which is better than a negative code.
Oh,
Hardware failure 5 and calibration error 2, calibration error 1, and no new messages. So let's look at it for, on the spectrum analyzer. It's pretty obvious what's not working. We want to go to 1 gigahertz. Here we go, and it's right there. I have a nice 1 gigahertz, and then you tune it down, and it keeps being fine until you hit. So at 400 megahertz is still okay, and then you go below. There you go. So at 380 it's good. At 370 it goes wild. It has a whole bunch of peaks. So it's the cutoff 375. And then it loses 10 dB because it goes into a higher harmonics. And so see, it's really bad. And if we put the scope on it, we'll probably see a very deformed output. We'll confirm that. Alright, so now I have it on the scope, and that's at 400 megahertz. And I'm going to go down, and it's well behaved until 375, and I bet you at 374 it's going to look ugly. Yes, there you go.
Man. Yeah.
Wow.
That's very ugly.
What's happening here? Very distorted. The frequency is right, but it has distortions to it. Look at that.
Yeah.
That is so weird. So my guess is that it's just whatever creates the lower frequencies. So these are newer instruments. They don't have component level schematics, but they have block diagrams, and that's the output section. And you can see that there is something that's specific for what is like 0.1 to 375 megahertz right here. Alright, it's about time to fire up the elevator music and explain how this intimidating instrument works. The difficulty in these generators is to synthesize as wide a range of frequencies as possible. In the case of the HP8664, this goes from 100 kHz all the way to 3 GHz with a resolution of, wait for it, 0.01 Hz. Yes, you heard it right, up to 3 GHz with a resolution of 10 mHz. Not bad, HP, Agilent, Keysight, whomever you are. But how is this done? Since we don't have the schematics of the instrument, we'll have to satisfy ourselves with this block diagram. Fortunately, it's quite helpful. The heart of the frequency generation is the tunable Yig oscillator. Yig oscillators are a wonder of microwave engineering and would merit a video on their own. They usually look like this, a small metal cylinder, usually feeling very heavy for its size. Opening them up reveals a large electromagnet that takes up most of the cylinder and explains the weight, and a small puck-sized RF assembly on top, which is the oscillator itself. The magnet produces a variable field that tunes the microwave resonance of a Yig crystal. Yig stands for yttrium iron garnet, a dark crystal with unique magnetic, electric and optical properties. A Yig monocrystal is polished into a small ball and is used as a highly resonant microwave filter in the oscillator. You can see the ball at the end of a white support stem in this close-up picture. The crystal ball resonance is not only very sharp, but can also be tuned over a very wide range. so it makes excellent ultra-low noise microwave oscillators. That is as close you'll ever get to a real magic crystal ball. Our oscillator is then inserted in a phase-locked loop, or PLL, which can lock its frequency with millihertz precision. We explained PLLs in another video which I'll link in the doodly-doo. However, as you can tell from the diagram, the Yig oscillator only tunes rather high in the microwave range, from 3 to 6 GHz. So how do you generate all the other frequencies down to 100 kHz? It's done by using high-speed dividers made with gallium arsenide transistors. Gallium arsenide is a high-performance semiconductor for microwave transistors, which are much faster than their silicon brethren. Dividing the Yig oscillator by 2 yields the 1.5 to 3 GHz frequencies, which is the top band of our instrument. Similarly, another divide by 2 generates the 750 MHz to 1.5 GHz range. Pretty straightforward so far. But what about the lower bands? They seem to magically appear out of nowhere from other blocks in the diagram. But in reality, it's the same divider trick all over again. Take for example the HF driver, which generates the 375 to 750 MHz band. If we look at the more detailed block schematic of the HF driver, we find the next divider that makes the 375 to 750 MHz band. Yet another divider is hidden in the low frequency driver module. It makes the 187.5 to 375 MHz range. Aha, below 375, that's exactly where our trouble starts. You'd be tempted to point an accusatory finger at that 375 MHz divider. However, and very curiously, our problem continues down into the next band, the 0.1 to 187.5 MHz band, the lowest in the instrument. And this low band is generated using a completely different technique in a completely different circuit. We can see that it is made by subtracting a constant 1 gig from the 1 to 1.1875 gig range in a module called the down converter. Such a frequency subtraction sounds complicated, but it is relatively easily achieved in RF using an RF mixer, as we also explained in the previous episode. And yep, sure enough, we can see the mixer in the down converter tucked in a module we haven't talked about yet. So this is our biggest clue so far. Our problem occurs in not just one, but in 2 bands below 375. So it most likely happens in a circuit that's common to these 2 lower ranges. Is there such a thing? And sure enough, there is, in 2 places. First, in the amplifier of the low frequency driver A5, right here, just before the signal comes out of connector J1. Both lower bands go through this amplifier. Very suspicious, that amplifier. But there is another place. The combined signal goes on to the output amplifier A7. Now, looking at A7, there is indeed an amplifying path specific to the 2 combined low bands. So our problem could be in that path too. So there you have it. After this early bout of elevator music, I'd suspect a circuit in either the LF driver A5 or in the output amp A7, since they are the only 2 modules that handle the 2 low ranges in combination. Let's see if we can test our hypothesis further. Oh, I see how it's doing it. It's mixing 375 to 750 MHz with 0.1 to 0.187.5 and getting the 0.1 to 375 MHz out. So either that or that. We should be able to see all the signals here and check which one goes wonky. And we're looking up the code, and 50533 doesn't exist. It's 50532 and 50531 and then just to 5060. So that's not very helpful. We were confused for a moment that our error code did not appear in the regular diagnostics, but we soon found out that there is another set of more in-depth diagnostic that the instrument can perform. That is, only after you have executed the secret HP Jedi maneuver. We would later discover that there is yet a third level of even more complicated testing you can do, this time involving some rewiring of the instrument. Okay, so we're going to run the internal diagnostics. So you have to put a switch here to 1, check that all the power lights are on, they are. So I have to activate special function 320, preset. All the juicy stuff is in special. You see special. Enter the very special number. Okay, we do the secret handshake 320. Enter. Press the enter key, which is on. Testing. And woo,
that was the display.
It's 12 minutes. And if it returns a positive code, it knows which module has failed. If it returns a negative code, it doesn't know.
Right.
5 minutes later.
Alright, and it came back, and it's the dreaded negative result code. It came back rather quickly. You said like 5 minutes?
Yeah, 5-6 minutes.
So meaning it can't isolate the problem. -5190-311. We'll see if that's referenced somewhere. 519
0311.
03. Output amplifier J5, which was actually one of our hot guesses. E7. And then maybe something that's common to this line, and that would be the output amplifier. And this is what the code says it is. So I would say we check here J5 if we get an undistorted signal, and then if we get a distorted signal here, well, something in here.
Yep.
Alright, I just have to find where it is. Alright, both the HP self-test and our own hunch converge on the same thing, with HP thinking it's the output amp. First, we are going to test what's going into the amp by disconnecting the blue wire, which should give us the signal as it comes out of the low frequency driver. Once again, that should be a combo of the two lowest ranges. If that's good, then we'll move on to testing what's on the green wire, which is the amp output. So actually I think I'll take it from the output of the low frequency driver here, 0.12375 MHz. J1, so that's before it gets sent to the amplifier, and that's this guy right here. Alright, so that disconnected, that connected to the SMC. You should get something on the scope if I go to, let's say, 350 megahertz. RF on.
Yeah.
Yeah, oh,
Okay.
that's not too bad. So if I go down in frequency a little bit, it's distorted. Ooh, and I'm on 50 ohm over here, right? Yeah, that doesn't look too good. 160 megahertz, and I am at 160 megahertz. So it's doing the right frequency, it's completely distorted. It's also many volts. Looks overdriven to me. $370 looks good. Then it changes range, right? At 380 it's gone. So that's a bit annoying. It's not clean getting into the amplifier. It's not as bad as what comes out. If you are close to 375, it's good. And then it grows. And I think it gets distorted. I am wondering if the automatic level control is not working. So kind of fortunately, they tell us that the level of the signal at the output should be 11.5 dBm. And I already know from the scope that I have more than that. And I have 16.2. And then if I go down in frequency, it just keeps growing. So I think we're just, look at that, I have 18, 19, I should be at 11. So I think we're just overdriving the poor amplifier. Oh my, this is going to be intense. So we are suspecting either of the orange modules here, one that combines the two lower bands and one that amplifies this combined signal. So we brought out the scope to look at the signal in between these two modules in the blue coax. We disconnected the coax and routed it to the scope. We got a distorted signal, but not as distorted as what we saw out of the instrument. Furthermore, as it got more distorted, its amplitude also went way too high. It should be 11 dBm and we got 18 dBm, which in linear terms is over 4 times too much. That makes me think that maybe the LF driver is working, but the automated amplitude control is faulty. To make matters worse, the amplitude control signal, called automatic gain control or AGC, is generated in A7, our next suspect module. So the fault could be in A7, cascading back into A5 via improper AGC level. These annoying looping circuits. One way to know for sure would be to feed A7 with a correct undistorted signal at 11 dBm from an external generator and look at the output of A7 on the scope. Somehow levels too high here, and it gets distorted, and it gets even distorted further down the output amplifier. So we can do another check on that hypothesis and go here, that's where a signal comes in, and feed it at 11.5 dBm and see if it comes out correctly out of the amplifier. So from over here with the pseudo-modern Keysight, we give it its 11.5 dBm requested to the amplifier. It's hooked up through my little test cable here, through, that's where the input of the amplifier is, and it comes out, I've set it at 0 dBm, and it comes out on the scope, and surprise, it's bad. And then I don't even have close to 0 dBm. Yeah, I have minus 10 dBm, I'm not even close to 0 dBm. Or maybe it's pushing because it doesn't have enough output. Then it's pushing the AGC up, and then it's driving the driver into over voltage, over power. That could make some sense. So then we would concur with the error code and think it's the output amplifier.
Right.
That's just not able to amplify the stuff. And then causing a secondary fault into the driver by trying to via auto level control, trying to get more output out of that driver. So right now we're giving it something at the right level, and we're getting something completely deformed. We know it works fine at higher at 3 gigahertz. So we know that the AGC works. We get 0 dBm on the dot on the higher sequence.
Yeah. So that means we can trust all of this.
Yes, correct. So looking at our A7 module, we give it the correct input and it gives us the incorrect output. By the way, have you noticed that there is a big bad error in the block diagram? The output shouldn't come from there after 2 rectifying diodes. Most likely, HB forgot to draw a wire to further confuse us. I think this wire is missing. That would make much more sense. The output would come this way out of the RF amps. The other path then, in purple here, is the power output signal detection by the 2 diodes, which is then amplified to generate the AGC signal. Note that it is split in 2. One part goes to control the gain of the higher bands, and the higher bands are working perfectly fine, so most of that purple path can be trusted. The other path goes to the lower bands AGC, and I bet you it's working perfectly fine too. It is just reporting correctly that the output is too low. which would mean that our problem is indeed the lower band RF amplifier, which is both not amplifying the signal and adding insult to injury by further distorting it.
So there's two buffers or amplifiers here. Or there's that.
Well, I think this is just not delivering enough power.
Probably, yeah.
Right, this is screwed up. It's that guy, most probably.
Right.
So out goes module A7. I feel like an auto mechanic. Mike, can you help me the rigid cable that's in my way, then this is in the way. Yeah, you just bend it. Okay. That's what you do with rigid cables. Okay, got it. Alright. That's it. Okay, there was less of a reveal than I thought. we have to open it up some more.
More screws.
Link. So it's from the 1990s. I'm not impressed with with the supposed improvements so far. Oh, here we go. All right. It was coming into. That's J5. Coming into J5.
That's right.
And oh, it goes into, and the output amp is inside that thing. It's a hybrid. So we're somewhat hosed.
Well, if that's the problem.
If that's the problem, it could be the power to it, or... Oh man, so there's going to be a fair amount of reverse engineering in it. Oh, there have been some repairs already. This has been repaired, U26 has been changed.
Yep.
This has been changed, which is just a connector. So we're not the first ones in this thing. This is made out of mostly commercial parts, except of course the parts that we are worried about. Indeed, after all this detective work, we end up in an undocumented board with a fault that could be in a proprietary hybrid. And you haven't seen the least of it yet, as I am about to make the situation a whole lot worse. Okay, let's go for another round of 10-minute calibration. Well, fellows, as I was just turning the camera off, it let the magic smoke out. To be continued in the next episode.